this exciting workshop this week. And good afternoon, everyone. Today, let me briefly introduce initial scientific results obtained with the 40-meter TNRT, International Radio Telescope, on behalf of the radio group of NARIT, Thailand. I'm Nobuyuki from NARIT, Thailand, and NOAJ, Japan. So the title of my talk is The Detection of OH Maser Emission in the 71-year periodic comet 12P Pons-Brooks using the 40-meter TNRT. The comet, the main target of this talk is shown by a photo taken by the NARIT Outreach Division. Also, our TNRT telescope is shown by the left photo here. So in the first half of my talk, let me briefly introduce my institute and our radio astronomy project. If you see this slide twice during this workshop, I apologize it, but let me briefly introduce this slide again. NARIT, National Astronomical Research Institute of Thailand. This is supported by our executives, the director Saram, the deputy director Wipu, the founder Professor Bunraksa. Also, we have science advisors such as Busaba from Max Planck in Germany and Malcolm Gray, a major theoretical researcher. And both of them are participating in this workshop this week. We have Center for Radio Astronomy and Engineering, CRAE, led by Dr. Koichiro Sugiyama, the manager of CRAE. Under the CRAE, we have two divisions, Thai National Radio Astronomy Observatory and Advanced Radio Frequency Laboratory. So there are several science commissioning scientists under the TNRO, me and our postdoc bank. We are also participating in this workshop this week. So this is our telescope, TNRT. We have so far received two receivers at L-band and K-band. The L-band receiver is installed at the prime focus of this telescope, while the K-band is placed at the Nasmyth focus of this telescope. So this is an upgraded version of ELS 40-meter radio telescope, but we have a special function called prime focus tetrapod head unit. So we can flip this THU to change the focus position from main focus to Nasmyth focus or from Nasmyth to main focus. The frequency coverage of this telescope ranges from 0.3 to 115 gigahertz. A surface accuracy of 150 micrometer is expected to be achieved for high frequency observations. The best pointing accuracy is expected to be about 2 arcseconds. This telescope is very fast. For example, an azimuth driving speed of about 3 degrees per sec can be achieved using this telescope. So we summarize science cases of the 40-meter TNRT in a white paper published in 2022. Anyone can download it from the archive. And it covers a wide variety of science topics such as the pulsar, high mass star forming regions, high mass star formation, active galactic nuclei, and so on. And many participants of this workshop kindly contributed to the white paper, so thank you very much. And also, this is our own telescope, meaning that this is very flexible. That's why we have the advantage of time domain sciences. For example, the lower panel shows the time variation of water 22 GHz water maser in a high mass star forming region. And also, we made an announcement for the call for proposals of TNRT Cycle 1 in the last December. And now the Cycle 1 science observations are running, and it will end in the end of August. Now, the TNRT L-band receiver is ready for science, but we have a lot of science commissioning items left. For example, K-band. This commissioning is led by our postdoc bank, and also many people are interested in polarimetry researches. So full Stokes backend should be also verified for science observations, VLBI. We have conducted VLBI fringe check observations among our telescope and our collaborator telescopes in the world. For example, German FSW 100 meter, Chinese big telescopes of the first and Tiama 65 meter. And also we are negotiating with other colleagues to expand this VLBI collaboration in the world. Also, we have CXK band receiver delivered from a Chinese institute, and now this is put in our laboratory at NARIT, Thailand. So we have to install this into our telescope, and also we have to verify the science capability of this receiver. And also we have not started to design the higher frequency receivers of Q and W bands, but we have a plan to install Q and W bands into our telescope in the near future. And from here, I'd like to move on to the main topic of this talk, initial scientific results of 40-meter TNRT. The title is the detection of OH measure emission in the 71-year periodic comet 12P Pons-Brooks using the 40-meter TNRT. Again, the left optical photo was taken by the NARIT outreach division using a commercial camera, and the telescope shows our TNRT and our TNRT site. So comets are fossils of solar system formation. It retains the information of early stages of the solar system, so studying the comet is important. And left panel shows the elliptical orbit of Halley's comet, and right one shows the anatomy of a comet. Comet shows clear nucleus and tails of ion tail and dust tail due to the solar wind and sunlight. And OH can be detected from the cometary atmosphere called coma, and OH lines can be detected at radio, optical, and infrared wavelengths. Today, I will focus on the radio wavelengths. And one of the most famous catalogs for OH 80 centimeter lines in comets is the Nancy database. Nancy Radio Telescope, NRT, Meridian Telescope, is located in France. It is equivalent to a 94-meter radio telescope with a surface area of 7,000 meter squared. And this telescope is located at a latitude of 47 degrees north. And Courvoisier et al. 2002 summarized the NRT observations of 53 comets in their paper. Based on the OH observations of comets, we can determine several physical parameters, such as the OH production rate, water production rate, via a proportional relationship, and also water expansion velocity. Since the water is typically the most abundant parent gas species, so OH observations of comets are important to derive a fundamental physical quantity of individual comets. Also, using the water expansion velocity, we can study the expansion of the cometary atmosphere. We can study the kinematics of individual comets. And TNRT is located at the latitude of 19 degrees, meaning that we can cooperate in all sky comet observations. So just in the last year, we started TNRT Cometary Database project. So far, we have observed a few comets using the 40-meter TNRT, for example, 12P Pons-Brooks, a Halley-type comet. Also, we observed another comet, C2023A3, a new comet discovered in 2023. And NARIT outreach division is very active for general public, and they have taken a lot of beautiful photos of comets, as shown by left photo and right photo. Also, we observed both comets using the 40-meter TNRT, and we detected OH measure emissions from 12P Pons-Brooks on 22nd, 27th, and 29th of March, 2024. The TNRT results of 12P Pons-Brooks were submitted to the Planetary Science Journal recently. Also, we succeeded in detecting the OH absorption from another comet, C2023. Also, regarding the 12P Pons-Brooks, we discussed the total visual magnitude versus OH production rate as a function of time. For this comet, it is known that optical outbursts have been observed in 1883, 1954, and 2023 to 2024. And these optical outbursts are thought to be involved in the rapid release of large amounts of gas and dust from comet's nucleus. Regarding radio observational results of QOH values of this comet, as you can see the figure, we have a few results obtained by TNRT and also optical telescope. Trappists have provided OH values based on their OH line observations at ultraviolet wavelengths. So the number of OH values, the number of OH production rate is now limited, but globally, we can say that QOH values are increased around the perihelion. The perihelion of this comet is shown by the vertical black line, and this tendency is consistent with previous observations of other comets. Experimentally, it is known that QOH is proportional to the heliocentric distance to the power of -2 to -4. So in our observations, we demonstrated that TNRT can observe comets, and we plan to observe more and more comets in the near future. So this year, we plan to observe few more comets. And based on the TNRT call for proposal, cycle 1 ID8, PI is me, and we have four co-ites. We got the 154 hours of TNRT time, and the first target is C2024 G3. And this is also a new comet, and since this comet is very bright in optical, meaning that OH laser detection is very promising. Another target is 210P Christiansen. This comet would be approached at the perihelion around November 22nd. Since this comet is not so bright in optical, OH laser detection may be difficult, but we will try to see what's happening. And also, we requested TO observations for a new comet if discovered in this year, 2025. So to be honest, we have got a lot of comet data using the 40-meter TNRT. If you or your students or your collaborators are interested in analyzing the TNRT comet data for research purposes, please contact me. I'm always welcome to collaborate with any of you. So let me summarize my talk. Today, I introduced two topics. The first is Thai National Radio Astronomy Observatory, TNRO. We operate the 40-meter TNRT, and L-band spectroscopy mode is ready for science. However, we have a lot of commissioning items such as K-band, Rostock's backend, 12BI, CXKU bands, and QW bands. Another topic is the science case of the telescope. Today, we introduced OH detections from two comets, 12P Pons-Brooks and C2023 A3. The results of 12P were submitted to a refereed journal, and other comets would be observed in this year. If you have any ideas about collaborations between us, please contact the manager of Center for Radio Astronomy and Engineering, Dr. Koichiro Sugiyama, or me. NOAJ NARIT MOA compliant behavior scientist, or we have a lot of TNRO colleagues and science advisors, so you can contact any of us. That's all. Thank you for your attention.
Thank you for that. And such an interesting application of OH observations to see them in comets. That's great. Thank you so much for sharing. Do we have any questions? While you're thinking of questions, I might just take this opportunity to mention that we have a session on Friday. It's in the program. I believe it's the second session. Second of the main sessions, maybe 22. I'm not sure what number it is, where we're going to talk about using the new Thai National Telescope. So that might be a great opportunity to also talk to Nobuyuki about his research and about the possibilities with this lovely new shiny telescope. Radame?
I have a question regarding the astrochemistry of formation of OH in comets. So yeah, that's my question.
Yeah, this is very good question. Yeah, even though I just started this research from last year, but recently many high frequency millimeter and sub-millimeter observations of comets are done using ALMA and other telescopes for studying chemical species of individual comets. So yeah, this chemical study is very hot science topic in comet field, if my understanding is correct.
Okay, thank you.
Do we have any more questions? Well, if not, then we might roll right on to our next speaker, which is Max, who's going to be telling us about Big Cat and observing with the ATCA.
Yeah, okay. So I'm just trying to, we should have tested it, but it actually worked. Um,
Are you able to share your screen?
I'm trying to do it. Yeah, we should have tested it, of course.
Do you want to send me your slides and I can share them for you?
So, okay, that's, yeah, I'll just have to rejoin, but it will be fine.
Okay. Well, Shinji?
While waiting for Marx, I have a question to Sakai-san. So it's good that yes, some people are observing planetary our solar system, and I'm doing by static radar using NASA Deep Space Network telescope, and we can transmit at 7 gigahertz, but we need receiver, somebody to receive at 7 gigahertz, and we've been using ATCA, a compact array, but it's very competitive to get antenna time sometime. And but it sounds Thai 40-meter antenna will be able to receive 7 gigahertz soon with C-band receiver. So that can be good collaboration. And also I'm impressed that you can also observe in optical wavelength, so optical telescope. So do you know if anybody is observing asteroids with that telescope?
Yeah,
Yeah.
NARIT has a 2-meter class optical telescope, but the comets what I introduced were taken by a commercial camera, very compact, say 50 centimeter or something. Very small optical camera was used to observe comets, but for research purposes, yeah, big optical telescope are not so big. Some small telescopes have been used to study comets.
And when would be earliest you can get C-band receiver operational?
Yeah, it's a good. We have receiver itself, but we have to install it into the telescope this year. And if everything is going well, we plan to do the first flight of our C-band in this year, and science operation would be starting from next year in ideal case. So yeah, thank you very much for suggesting collaborations between us using the C-band. Yeah, thank you very much.
Yeah, okay. Maybe we should plan meeting with Sugiyama-san and you sometime in
Yeah,
future.
thank you very much.
Oh,
Thank you.
thanks. Yeah.
Okay, can you see slides now?
Oh yeah, yeah.
Okay, so I'm ready to start. Yes, so for this minor technical, I'm going to tell you about actually recent upgrades, which and I expected that many users of Compactor will on this meeting. So my talk will be virtual science, technical stuff, but I get to let the community know about Big Cat and how it's different from the system we used to have, so people at least will have a bit less anxiety next time they're. So if we go any further, like a bit of a disclaimer. So I'm just helping to commission Big Cat, and therefore I'm giving this talk in a bit unusual role. Commissioning instruments is sort of usual, but I haven't developed any single line of the code for Big Cat or wasn't participating in any decisions about design, how it's done. But in any case, I think I probably would have a habit of being biased towards the things how I would do it. So if there is any doubt, believe real developers, and the list you can see on your screen now. And in particular, Chris Phillips and Jamie Stevens should be able to answer most of the questions. But I will, of course, ask me after the talk, and I'll give it a try to answer as much as I can. So we have several interferometers available for general use, or 2 to be exact, if you don't count VLBI. So they both, like, of course, radio interferometers are machines which do imaging indirectly. So what we measure is correlations between voltages, and then we produce images in software. And that's why that particular path and how you do it is actually quite important for interferometers, probably more so than for single dishes. So we have Australian Square Kilometre Array Pathfinder, ASCAP, which was mentioned a few times, and Australia Telescope Compact Array, TCA, which I'll talk about. So these 2 telescopes have notably different operating model. So for ASCAP, first of all, ASCAP is a wide field low frequency survey telescope. It has very small number of operating modes, and the data are both taken and processed for you. So essentially, astronomers work with science-ready data. Of course, like during the initial phases when people are testing, there could be like back and forth on like various ways we're doing it, or testing, or getting your hands dirty with the actual data reduction. But in principle, what you get is the image or image cube. With compact array, it's different. It's very traditional telescope, and it's run by user in many aspects. We even operate it like observed by the user themselves. And obviously data reduction is also the responsibility of the user. So that's why what I will tell you about how the new system is working may be important for the actual users. And by the way, our proposals, like we can submit proposals for, well, for compact array definitely, and from time to time for ASCAP as well as guest science, but most of the ASCAP time is going to predefined surveys which were like approved long time ago. Anyway, on this link you can actually see like when the next deadline will be. It will be in December. Unfortunately, it just passed, but December deadline is also a millimeter deadline for the winter time in Australia, which might be helpful for many people. So first, a few words about receivers, because they essentially don't change with the upgrade. So compact array has a very good suite of cryogenically cooled wideband receivers. So they like all receivers combined cover frequencies from like 1.1 to 105 gigahertz, and of course there are some gaps. So most of the receivers have bandwidth of about 8 gigahertz. Of course, at low frequency you can't fit 8 gigahertz. That's why it's like from 1.1 to 3.1, our L-band one. And in general, as I said, like most of these receivers will stay, but there are additional components, the RF module to be exact, which is going to be changed in the later stages of Big Cat upgrade. And in particular, so currently the 4-centimeter receiver can go only up to 11-ish gigahertz, but it will go up to 12.3, and it will allow us to observe class 2 methanol transition at 12.2. But I guess, unfortunately for the participants of this workshop, no excited to H at 13.4. So all other bands remain the same. And for 7mm, some of you may know that we actually have tuning restrictions. So all frequencies are available from 30 gigahertz to 50 gigahertz, but not all of them can be observed simultaneously. And that restriction will remain for the time, for foreseeable future. So a few words about what we used to have. Well, in fact, actually our previous backend, which is called CAB, compact array broadband backend, which was the first upgrade, really broadband upgrade, where we could do like big bandwidth in one go. So currently we still have like 1/2 of the CAB remaining, and in principle it could be used, but it's not offered scientifically, but we can use it to compare Big Cat with this system. But it will be removed in like very near future, hopefully. So anyway, so this original, well, previous, current, whatever you can call it, backend had two gigahertz window, or sometimes they called IFs. And it's some people call it IFs, although in fact it's not necessarily IF. Because for say 4-centimeter band we have direct ingestion. It's not there is no LO. So these 2 gigahertz IFs can be placed anywhere within 8 gigahertz band, and optionally in each IF we can have up to 16 zoom windows. Zoom windows are narrow bands. I illustrated here. Like if you want high resolution, then the system can deliver across the whole band. Then you put zoom band where you want. And for CAB, it had like fixed 2048 channels. You put it where you want, and there are 16 bands per IF. Unfortunately for CAB, both positioning and of the zoom bands and the choice of resolution was somewhat restricted. So they could be positioned with the accuracy of half of the width of that zoom band. And there are only two modes which were implemented, what we called 1 megahertz and 64 megahertz. That is the resolution of the wide band window. And the zoom bandwidth of the single zoom window is tied down to the bandwidth of the channel. So it would be like 1 megahertz, like 2048 channels across 1 megahertz, or 1048 channels across 64. In particular, it could be very problematic at 12mm because it's one will be too fine resolution, but too narrow bandwidth, and the other would be too coarse resolution. So it was definitely a problem which will go away with the new system. But one of the interesting features of CAB, which we wouldn't have in the new system, is so-called seamless stitching. So we could put several bands in this sort of order, interleaved order, and in this case, the gaps essentially will be not an issue. So the system will take only, the channels are not independent, so it's identical signal, but there is no roll-off at the edge. So you would see as a user just a continuous band in this particular case. With the new system, if for some reason bandwidth of current options will not be enough, then technically this will not be available, but there will be some gaps or something that has to be done about it. But I don't think it is a big problem because the new system is much more flexible, and certainly we can have zoom windows with various parameters or on request and so on. So also that CAB system was the first time in the compact array history where we didn't have to make a compromise between resolution and polarization. And in particular for mainline NOAJ, well, I've heard statements that basically with previous system, it wasn't useful to do a NOAJ. So with CAB, it was possible essentially for the first time. With new system, of course, it will be even better. So what's the new system in a nutshell? So it's called the Broadband Integrated GPU Correlator for ATCA, so acronym of acronyms. So as the name suggests, it's a GPU correlator, graphical processing units. So there are two parts, as I hinted earlier, of this upgrade process. So we are currently in the phase 1, where we essentially reuse the existing infrastructure in terms of the receivers and RF chain and so on, install new digitizers. It's called so-called gimbal board. There are two options planned, 8-bit and 16-bit. Only 8-bit is implemented now, but 16-bit is coming soon. So what this part is doing is essentially coarse channelization. So all bandwidth will be chopped into 128 megahertz bands with oversampled polyphase filter banks. And then the data will be streamed over conventional 100 gigabit Ethernet. And the rest of the equipment is essentially commodity network hardware, GPU cards, and computers and switches. So essentially, we're using the commercial technology to do all the routing and the hard part. And because of this flexibility and because the fact that it is a software correlator, technically it is, well, everything is possible, whatever the machine can do for you in terms of the performance. At some point, we could start running out of, say, writing speed to store the data and so on. So that's why we cannot, say, do very fine resolution across the whole 8 gigahertz band or 4 gigahertz initially. But it will be much more flexible. So changing the mode is essentially one number. And with Big Cat, one of the issue we had is basically there were lots of bugs in the system which no one could fix because engineers who developed it essentially retired. So we were stuck with it. So with the new system, new modes, if new science appears or whatever, or just you don't like whatever we offer initially, it could be done reasonably easily. And moreover, if some interesting non-standard processing will be required, in principle, one can think of writing own software and running on this machine, working on voltages. Also, this particular design allows other modes, not just traditional correlation of voltages, but say tide array beams for VLBI. So we will be from early days, we will have essentially ability to record tide array for the whole bandwidth we have, which is great. And in principle, the same design can be exported to other telescopes, just a question of funding and so on. So as a second stage, we will have RF module installed that will give us 8 gigahertz bandwidth. So currently, we have two IFs of 2 gigahertz, and that thing will remain. But with the upgrade, we'll get additional 2 gigahertz, so we can cover all 8 gigahertz. And I forgot to mention that 16-bit quantization mode for gimbals is actually very important at low frequency where there is more RFI. But up there, we don't have big bandwidth, so we can actually squeeze more processing if necessary. It's not working yet, but will be soon. So what you get in the wideband data, it's presented as 15 sub-bands, 128 megahertz. So of course, the system does nice round number of 16, but unfortunately, it's not right down at DC. So there is a bit of basically the 0th band is unusable, doesn't have anything which you can use for science. So we have only 15 sub-bands, and it actually gives 1920 megahertz only, so slightly less than 2 gigahertz. So initially, before the full upgrade, it will be a bit of a reduction of the full bandwidth. So there we have oversampled filter banks, so all these sub-bands, they're a bit overlapping here. Don't worry about the gaps, so hopefully they'll go away, but it's good to bear in mind that all of them are processed separately and go through different paths on the system. So it is possible that will get some effects at the edges, which may require some calibration or something like that. But if everything goes well, normal bandpass calibration should take care of it. So in terms of the spectral resolution, the default continuum, which is currently planned, is 1 megahertz. That's the data you see. That's almost 2 gigahertz at that resolution. In principle, higher modes are available, and even now. So what is currently promised is down to 9 kilohertz across the whole band. And that gives you about 1.6 kilometers per second at 1.6 gigahertz. Probably not great, well, definitely not great for masers or even other galactic stuff. But at high frequency, you might not even need anything else because it's like 0.12 kilometers per second at 22 or less than that at 44. So at higher frequencies, we can just observe without zooms and you don't need to worry about anything. So if you need high resolution, then you can put zooms. Similarly, as for CAB, they are in addition to your continuum channel. So you get this, plus you get zooms on top. So you can position them where you like, but the system itself allows multiple modes, as I said, but at least initially it will be restricted to the number of modes tested, verified by system scientists. And at this stage, whatever is planned is to have 4 zoom bands within each subband. So every 128 megahertz will have 4 zoom bands, say 2 megahertz, or give or take factor of 2 or 4. And similarly with the resolution, so we can definitely do CAB's current best 488 hertz resolution, or maybe a factor of 2 to 4 better. So I think Chris told me that actually he tested down to 1 kilohertz resolution, but maybe at lower frequency where we can squeeze more bandwidth and do a little bit more, or squeeze more processing because the bandwidth is smaller. So anyway, with zooms at 1.6 gigahertz, you definitely need zooms at 1.6 for masers. You will get sort of good resolution what we have now, and polarization also comes for free. So one thing I forgot to say earlier, because of this being slightly less than 2 gigahertz, in principle, there could be gaps here when we try to feed bigger receiver band with this thing. It's not impossible to consider other ways to actually make it tunable, but I don't know how quickly this particular thing will be implemented, or if at all. So it is possible that these setups have to be iterated a little bit when we start doing at least science commissioning. So changes. First, access to the system will still be via VNC window. If you're familiar with compact array observing, you know that you actually start the VNC on the machine called XBones at the moment. It will be Skull instead of XBones, but that particular thing doesn't change. And there is no need for second VNC. We used to run the actual correlate in a separate one, so now it's all done in the background. Maybe there will be a terminal, like at least initially, just in case something hangs and needs to be restarted. But that thing is simpler. As before, you would need SSH tunnels to get for the external access outside of CSIRO. And here I'll make a point that from the 1st of July, actually, both SSH keys with passphrase and the password will be required to access our gateways like Venice. That's sort of Australian government requirement of being sort of two-factor authentication. So anyway, if you have account on Venice and haven't set this up, I suggest you to log in before next Tuesday and set this up, because after that time, you will have to involve some third person to put the SSH key in there. So, and moreover, this particular setup might upset some VNC clients. I honestly never seen a machine with that particular setup, so I'm not sure that if you use some fancy VNC client that it will deal with it, or whether it would distinguish the passphrase from a password. But if you do it manually in a terminal to create SSH tunnel, it should work. And after the observations, the data will be available in the archive as currently is, but the archive will be different. So it will be CASDA, same archive as for ASCAP data, instead of current ATOA. And the historical compact array data are being migrated now. So you can use this link to get you set up with CASDA. So CIOps, as I mentioned, we do observations essentially in person manually. Well, we don't necessarily come to Narrabri or Marsfield anymore, but you interact with this program, which is called CIOps. So there is a new CIOps in the new system, but it is intentionally somewhat similar to the old one. So I can tell you that it probably took me like few minutes to understand what is where, being familiar with all systems, so don't stress too much. And all commands are pretty much the same, so even if some bit of documentation is not updated, don't worry. The old one will still work. It has more monitoring in it. So in many cases in the past, you would have to involve some other software, some other monitoring software to check what the array is doing. And there was also a separate text-based app, which was called Assistance. So now we probably don't even need this because all this info is captured on this single application. And by the way, it's just a client now, so all work is done by the server, so you can run multiple copies, so you can kill, exit, whatever, and that shouldn't affect any observation. Hopefully that's not related to CIOs, more like the system-wide, but I couldn't find any other slide to mention it better. So I would say now that hopefully we wouldn't have delay jumps and no need for decal, at least in routine observing. So maybe when reconfiguration happens or some other firmware work that will be needed, but not routinely. So we actually could expect that for various say variability studies or something like that, where we can essentially automate observations and use like very little time, we wouldn't need to do this setup, so that would remove the manual part or part which is harder to automate out of equation. And moreover, for things where I don't know something flares and you want to go to that source quickly, you can always override the observation, well, provided all these grades in the proposals are right. I think similar mode was already tried now, but if you use a particular strange zoom configuration in the past, basically it couldn't be overridden with a different kind of observation, which also required entirely different setup. So yeah, I think in terms of the efficiency of using of telescope time with a new system will be much better than we used to have. So other tools for online monitoring like VIS and SPD, you might be familiar with, they're also changed, but their look is similar. There is also a tool now which is called SSPD. So in fact, it's the same as SPD, but it used to monitor so-called sub-integrations. So the new system, it doesn't have a fixed cycle the same way as traditional hardware correlators have, when it's like every 10 seconds it spits out the new correlations. So the system works at much faster cadence, and then averaging to requested cycle time happens in the ingest before the file is written. And as a result, basically you can monitor the data coming from the telescope at the very fast cadence. It's configurable, but what we used so far in the testing is about 0.2 seconds. And then it averaged to 10 seconds. So, and in principle, as I said, additional averaging in both time and frequency can happen in ingest. And in particular, we could do some flagging before this averaging happens. It may be a bit dangerous because like potentially it creates some other systematics, but it also won't be available on day one, so don't worry. Positive thing about this is the system will be much more responsive. So currently when you start observation, it might take like 3 cycles, about 30 seconds normally, before it actually even responds, even if it's on the same source. With new system, it will be semi-instantly. So again, better efficiency, probably less overheads, especially for like some stuff where you have to move continuously or like maybe even mapping projects. So the biggest change users will encounter is probably with the scheduler. So of course it's a new system, the new scheduler. It's also a web-based thing. I can't say that I'm 100% happy with it because like every time I look, I found something I'm not happy with. But we'll probably need a few iterations on it when science commissioning actually starts. So yeah, here you can see how it looks like. That's the address. I don't know whether it would work now. You can definitely normal logins wouldn't work because the access has to be requested separately, but eventually if you can log into the system, you would be able to log into this thing. So things I'm constantly tripped with is that it actually has like separate pages for source list, for correlator configuration and actual schedule. The idea is that they could be reused between multiple projects, but I found that it's a bit, well, sometimes basically I have to double check what is actually in use. The other thing is there will be more access control. Again, we have to see how well it works, but looks like it's just a modern world requirement that the old-fashioned system where basically everyone shares the same space, we cannot, well, not allow it to live in the same mode anymore. So, and as a result, for example, with support, it's a good question how it will actually work, because like if someone calls on 3 a.m. and said like something doesn't work and we want to see what the schedule looks like, we might not necessarily be able to access other people's schedules, but that particular worry was reported and hopefully some solution will be found. But on short notice, there could be issues. So with Zooms, I mentioned to you that they're all like we have the fixed setup across. So essentially all 128 megahertz will share identical setup. It doesn't mean that there will be same arrangement, so they can be at different frequencies, but at least the number of zooms, the width, and the resolutions, which technically could be different for different zooms, that will remain fixed. They don't necessarily have to be active. So they could be like here, say one zoom here, one zoom there. Well, that's technically the same configuration, but I could put another zoom here and that would be fine. But I can't say, a wider zoom here and narrow zoom there. That wouldn't work. Yeah, there is a nice velocity calculator, although I do have problems with it occasionally, but that's allows you to plan reasonably complex observations. Like if you have many masers and want to observe them with very high resolution and need to worry about like tiny details, like on what day you observe that particular source. So technically it could be done in this tool, although I still think that the old scheduler sometimes is easier to use. So there are additional features in the scheduler, so it can be used to assist planning. So you can visualize, for example, source elevations and so on. You can plan, simulate UV coverage. In principle, I think what I've seen that you can just give the commands, similar commands as you would give to CIOps, and it will simulate you how the observations will look like. And by the way, in the scheduler for each scan, we have to, or should give intent. So we should say, this is my calibrator, this is my target, this is my bandpass calibrator, this is pointing. So in principle, the old system had something similar, but it was much more abbreviated and sometimes people didn't use it right. So in the new system, it will be much more obvious. So there is also a tool to plan mosaics. So in the past, people always did mosaic planning outside of our software, say in Myriad, Taskmos Gen was often used, and many people who did mosaics regularly actually use their own scripts. So the old formats are still accessible, and the scheduler will convert them to the new format, but you could also use the like built-in features, essentially, if you want to cover a certain area with at certain frequency, it will calculate all these, Nyquist separations for you and will do the right thing. So another big change, the data format. So the old system used to write so-called RP feeds, which is proprietary ATNF format essentially, which is very old and designed for old system and so on. So the new system will write ASDM, so that's the same format as ALMA is using, but of course, like there are some minor changes related to different telescope, and in particular, CASA as not patched version, but the CASA installed the standard way wouldn't be able to handle it. So unfortunately, at least initially, before all these patches are reported, propagated, and so on, a specific version of CASA is needed. But it will be provided on one of our machines one way or another. So you can't do much with ASDM as such. So here I just showed how it looked like. It has several metadata tables, which are just plain text, and then directory with binary tables. So the initially conversion will be needed with this custom version of CASA. So very simple script, which I showed here, will convert to measurement set. And then if you want to use something like Myriad rather than CASA, then you can convert that measurement set to UV feeds. It's interesting question, what survives the conversion? That's always a problem in software when you use multiple data formats and multiple conversions. I guess stay tuned, be very careful when you do it for the first time. So hopefully a lot of these problems will be polished during science commissioning. And finally, a little bit of science, especially because bit of a negative point, we wouldn't be able to do it with Big Cat anytime soon. So for many years, we actually ran a legacy project, which we call Starfish. So it's actually a 7mm project where we use compact array as 6 single dishes. So some of you might know that we used to have a telescope called MOPRA, which was extremely popular among people who study molecular lines, thermal lines in particular. Essentially, it's a single dish with very good spectrometer. So we don't have access to MOPRA anymore, can't get time on it. But we tried to use compact array with Big Cat to use it as essentially a single dish. So we could have set it up maybe as 6-beam multi-beam, because for single dish we don't actually have to point all 6 dishes into the same part, but software-wise it was easy to point them to the same point. And then we developed the scanning. Well, in fact, scanning on the fly scanning was a standard mode, but all processing, scheduling, and so on, we had to develop all custom software, just the group members. And that allowed us to actually make map at that 7mm band. And you can see here all these molecular transitions which were included, and an example of the map with 44 GHz masers. Their positions, of course, it's single dish data, so ideally we want to follow the map with interferometer as well, but single dish, well, it has its own advantages for thermal lines, simply because compact array doesn't have too many antennas, so brightness, temperature sensitivity is not that great, but single dish doesn't have this problem. And even with CAB, we could actually use the power, like how many zooms we can observe and simultaneously, and the wide bandwidth to actually capture all that lines. So in principle, Big Cat even will have some special mode which captures only autocorrelations. It's largely done because in principle this system can be exported or used on other systems, including MOPRA. It's all question of funding. But with our system, with compact array, we can get 8 GHz bandwidth eventually, even more lines, more transitions can be observed simultaneously. So there was definitely an interest in the community to do Starfish-like observations at other bands or other sources. Unfortunately, it's not happening anytime soon, simply because a lot of software was non-standard even, and it has to be rewritten for the new system. And I can't even estimate how much effort it will be required, but yeah, stay tuned. Maybe eventually one of us will do it. And finally, instead of the summary, I just list again the benefits of the new system. So hopefully it will be more user-friendly and with less bugs. Definitely new modes could be implemented if necessary. So we will have better spectral resolution options, especially for 12 millimeter. And at higher frequency, maybe people don't even need to use zooms. That will simplify planning enormously. And observations themselves as well. So potentially we could even have different spectral resolution for masers and thermal lines or radiochromination lines. But sometimes in the future, this will not be available from day one intentionally. All support is in the software. It's just will be enough for simplicity, at least initially. So it will be much more flexible in terms of the positioning of zooms. So we basically don't need to capture like more bandwidth than we actually need for the science, and better default resolutions and things like that. So the really new capabilities will come with RF upgrade when we can actually do much better than we've done before. And basically for spectral line observers, more bandwidth means that we can observe more stuff simultaneously in one go. And we can finally get to 12 gigahertz methanol lines. So can do surveys if we want to, although it's a good question what actually makes sense. VLBI, but of course we need other antennas with 12 gigahertz as well. And we can do monitoring together simultaneously with 6.7, 6 gigahertz excited OH and so on, and other lines which will fall in the band. And I'll stop here.
Thanks for that, Max. But it's so many changes.
It is many changes, yeah, but hopefully I would say, well, I don't like to say people here, it's just points to think about. I guess if there are people very familiar with compact array, they would see immediately like where the changes are, and hopefully it will alleviate the anxiety. But if, of course, like people not familiar, then it doesn't matter. They still have to rely on support, which of course will be provided by us eventually. I guess the biggest issue now is like our people have to learn the system. And I must say, like 4 months ago, I knew virtually nothing about Big Cat. Could probably do something like this myself, but at least I didn't know how it was done before I had my hands dirty and could play with the system.
It kind of leads into a question that I had actually. I was wondering if you guys are still doing regular training sessions.
Well, I suspect what happens is when the system is ready for science commissioning, which, well, supposed to happen in April, well, initially in February, but yeah, you know how it is. Anyway, so that's when the science commissioning happens, we get the pool of experts or sort of people who understand at least a little bit more, and then the training sessions, other things will happen. So I would say observing with the system, probably people will need a bit of the training with scheduler. Well, maybe I'm becoming too old, but I can't say that a lot of things in that scheduler were very intuitive for me, at least. So, playing with it, I did manage to lose the shade, like all the work I had and things like that. So during my early commissioning experiments, I actually ended up just editing the schedule files like in text editor, because they are just JSON files, so they can be hand edited. At least with current modes, that seems to be like basically there were bugs in the system, and now, well, they are being fixed, but like we recently had a bit of a scary situation when some vulnerability was discovered. So I suspect because of this, some parts were disabled. But of course, when you have the system with multiple parts and some of them don't talk to each other, the behavior was strange. I probably tried to use it exactly at that moment, so without knowing all these things. So yeah, all this. They may not necessarily be problems, like big problems, but they're certainly annoying unless you know what's going on. But yeah, once we have enough people, they can advise on sort of science processing part of it, and how to deal with ASDM files and that part of thing. Observing pretty much the same as before. It's just, with the old system, I knew all the bugs. pretty much. So I kind of knew what to advise people to, like, where to look if something happens. New system will have new bugs, so it will take a while. Of course, like within couple of weeks or whatever we have for science commissioning, all of them will not be found. And in particular, when we do something non-standard, like high frequency observations and high spectral resolution observations. So this thing can be dangerous. But in terms of interacting with the system when the schedule is ready, I would say you will pick it up straight away if you used it before.
Does anyone have any questions for Max?
And I forgot to mention, if you want to ask something about ASCAP, feel free. It was nothing in my talk, but I can probably answer.
Well, I'll ask one more question. I feel like I think I know the answer to this, but I want the answer to be different. Are there any plans to make any changes to the interface for the ATCA?
So what do you mean the interface? Just compact?
Wrapping it in something more friendly.
So by the interface you assume ATCA, sorry, CAOps?
Yeah.
Well, it's different now. So if you want something web-based as opposed to text-based, in principle, yes, it could be done. Maybe eventually, because like this thing is client, so it can be done easily. It wouldn't affect anyone else. If people like text-based, they can use text-based. I suspect it's just a question of having time. In principle, for like simple projects, well, even for less than simple projects, I suspect the way we're going, it very soon will be semi-automatic observing. So unlike the old system where, well, the big thing were bugs, basically, like if you use all what's capacity performance, like every single bit of performance of cab with all zooms, it will, well, never last 2 days from my experience. So usually you will get a failure, and quite often a few. So basically you cannot leave it. If you go away quickly to have lunch, like that's sometimes it will fail right at that moment, and well, you basically will lose time if it happens. So hopefully new system will not have it. And because we also don't need to set it up, you observe calibrators, but that's in your schedule. So essentially you can think of mode where you don't need to observe, you just submit the schedule and it does everything for you. So I think we're pretty much there for like transient science done in continuum. We probably never tried it for spectral line. And obviously at higher frequency, I personally would worry more about the weather and that it's done the right thing. I guess possible to put all these constraints and things like that, but knowing how it is, if the robot doesn't care about your observations, you do. So when you see that, okay, like I don't want to go to this source now, it's too early, or to like whatever, or I have like a shower cloud coming or something, like you may change things, but of course, in most cases, people just calibrate and then start their loop, and then that's it. Maybe 1934 at the very end for primary flux calibration. So all that stuff can be automated even now. So yeah, I suspect probably will be no interaction and just automation. Similar how it's done at ASCAP.
Yeah, that would be nice.
And for monitoring, it's actually great because in the past it was more difficult. Well, the major monitoring project I mentioned, I forgot when, maybe today, maybe yesterday, but I've only used like 2 hours of compact array time, like every month, but over many years. So in principle, something like that. The biggest issue was actually be in the place with internet, plan my flights around it the right way, because internet is not always available and this kind of thing. But with new system, I don't see why it can't be just pre-programmed if it's in there. you could do even dynamically. If there is a gap, just do it.
Mhm.
So I suspect we'll have much less so-called green time with gaps, simply because people who don't care about UV coverage, although for interferometry you typically do, but if you don't need an image, if you do maser monitoring, you can get away without it. So in the past, like, well, I always asked for green time if, you know, I had something to do. But sometimes, you know, I had to wait for correlator to be in the right mode because it takes a while to put carbon given spectral line mode, about an hour. And quite often, again, if I'm in Narrabri, then not a problem. If I'm somewhere else, then technically I cannot just say I will do it, because there are some hard lockup modes where someone has to push buttons on site. And that means, you know, extra pressure on the local staff. Plus, if it's 3 a.m., it wouldn't work. With new system, hopefully, it will all be, you know, computer will do it for us. So I think it will be easier. But of course, if it's easier for everyone, it means that getting the time will be even harder. That's the negative side of it.
Yeah, no worries. Thanks for that, Max. Does anybody else have any questions? Well, there's always the Slack channel. So if you have any questions or want to further any of the discussion or well, anything about ATCA or the Thai National Radio Telescope or comets with Nobuyuki, you can take that over to Slack. But yeah, I think we might just end the session there. So let's thank our speakers, Nobuyuki and Max, again. Thank you very much. And we'll see you all in the next session. Bye-bye.
So
Bye-bye.